Okay, so I'm going to go over a geophysical fluid dynamics practice final exam at the graduate level. I'm going to go over this very quickly. Um, so you have the setups for how to do these. Okie dokie, let's get right into it. Number one, consider a rotating stratified ocean with Cartesian coordinates x, y, z, where z is the vertical positive upward. Assume steady large scale flow. Horizontal momentum equations are for this negative f of v here, and for this for our f sub u here, and the vertical momentum equation reduces to hydrostatic balance. So taking this into consideration for letter A, starting from full vertical momentum equation, derive the hydrostatic approximation for this partial dv dz equals negative rho g. So here we go for this geostrophic and hydrostatic balance. Vertical momentum equation is determined by this. Okay, for large scale geophysical motion, vertical acceleration is usually much smaller than gravity and the pressure gradient forces. So we wind up with this rho dw dt is approximately 0. So therefore, right here, our 0 equals this equation. So we're going to wind up with the following partial here, for the following derivative here. And this is our hydrostatic balance. For part B, suppose the pressure field is P of x, y, z. And here we have pressure and density. My apologies, in the previous video I kept saying momentum. I had a real bad headache, and I was talking about different physics topics involving momentum the day before, so I guess the two got conflated. I also kept talking about iota, I believe, where I was talking about iota the day before. It's just strange with things, the variables play tricks on me sometimes. So here we go. That's our pressure field. A is constant. Determine the geostrophic velocity components, that u sub g, v sub g. So here's what we're given. Take the two partials with respect to x and y. We get a, y, a, x. Here are our geostrophic relations. And we wind up with our v sub g and our u sub g. And those are our velocity components. And for letter C, discuss physically why geostrophic balance is generally valid for synoptic, scale, atmospheric, and oceanic motions, but not for small convective motions. Okay, this is a good conceptual one, textbook stuff here. So geostrophic balance is valid when the Rossby number is small, RO here is equal to U over FL is much smaller than 1. This means the Coriolis force and horizontal pressure gradient force dominate inertia. And you have your synoptic, scale, atmospheric systems and large scale ocean currents. They often satisfy this. Small convective motions have smaller length scales and larger accelerations. So our RO approximates 1 or larger. And in that case, inertia is important and geostrophic balance fails. Okay, so that's number 1. And I'm going to go through this quickly so you have a reference if you try this, and you could just check your answers. The math and explanations work out. Pardon me if I mispronounce anything going fast or misidentify a variable. It happens. Human user error. Number 2, consider a shallow water fluid layer depth of h of xyt on an F plane. Shallow water potential vorticity is given by this. Q equals zeta plus F over h, where zeta is the relative vorticity. So we have here letter A, starting from shallow water equations, derive the materially conserved PV equation, dq dt equals 0. So here we go. Here's the shallow water equations. All right, this is textbook stuff. Okay, we're going to take the curl of these. To take the curl of the horizontal momentum equations, rather, gives the vorticity equation. This is right here, and that's our zeta plus f d zeta d dt of that zeta plus f, and that's going to equal that negative zeta plus f del dot u, and from continuity, dh dt equals negative h del dot u, and now we define that q equals zeta plus f over h, and then we have the following, this dq dt 1 over h, ddt this of the zeta plus f minus zeta plus f over h squared dh dt, and we're going to substitute the dq dt equals 1 over h, and we're going to substitute, and dq dt is going to equal this whole thing. I'm not going to say the whole thing. By the way, that's a zeta right there I'm pointing to. Sorry about my horrible drawing there. And these terms are going to cancel. We're going to wind up with dq dt is 0. Okay. And B, fluid column. And I omitted a lot of intermediary steps with the algebra and computation. So B, a fluid column initially has depth h naught and 0 relative vorticity. The column is stretched so that its depth becomes 2h naught. Determine the new relative vorticity. So initially we have q sub I f over h naught. Final, we have q sub f is that zeta sub f plus f over 2h naught. And then we have PV conservation. We're going to set these equal together. The initial, proportionally, initial is going to equal to final. 2f is going to be equal to that zeta sub f plus f, and zeta sub f is f, so the column gains cyclonic relative vorticity. So here, explain physically why vortex stretching produces rotation and rotating fields. And in C, textbook conceptual answer, if a rotating fluid, let me read this again. Explain physically why vortex stretching produces rotation and rotating fluids. Okay, and this is a potential vorticity conservation problem, so we have to, I should have been more mindful of this. So if a rotating fluid column is stretched vertically, its moment of inertia decreases to conserve absolute vorticity relative to its thickness. The column spins faster. This is the rotating fluid version of angular momentum conservation. Okay, so that's good for that one. So number 1 was geostrophic and hydrostatic balance. Number 2 was potential vorticity conservation. And now we move on to number 3. And number 3 is going to be a Rossby conservation problem. Okay, so here we go. So consider linearized barotropic vorticity equation on a beta plane here. Here's what we're given. This should look familiar. And assume the wave solutions of this form we're given here. Should look familiar. Derive the Rossby wave dispersion relation here. So here we go. Rossby conservation. So the governing equation is the following. And we're going to use this size substitution. And then we're going to use this del squared psi equals that negative k squared plus l squared quantity psi, and then also d dt psi d dt del squared psi equals iw k squared plus l squared, that quantity psi, and then beta d psi dx equals I beta k psi, and then this I omega, I shouldn't say w. See, there I go again, mispronouncing, going too fast. Omega, right? Okay, so I omega k squared plus l squared psi, that plus that I, this is going to be a beta k psi equals 0, and we get, we just do the algebra, isolate omega, and we're going to get negative beta k over k squared plus l squared. Okay. So Here, for letter B, show explicitly that the zonal phase velocity is westward. C sub x equals omega over k, that's negative b over k squared plus L squared. And so C sub x is less than 0, so the Rossby wave phase propagation is westward. Okay, compute the group velocity components. Group velocity components right here. C sub gx d omega dk, C sub gy d omega dl. Since omega is negative beta k times the quantity k squared plus L squared raised to negative 1. When we perform our differentiation, we're just going to get for C sub gx, we're going to get this. And for C sub gy, we're going to get this. Okay. Part D, discuss the physical origin of Rossby wave propagation. So conceptual one, textbooks, Rossby waves exist because parcels displaced north or south conserve potential vorticity while F changes with latitude. This produces restoring vorticity anomalies that propagate as planetary waves. Okay, so that takes care of number 3. Again, I'm going through this quickly. I skipped some steps because I want you to just have like a reference if you want to like practice these and then check your work or whatnot. So number 4, we have consider a continuously stratified Bussardesque fluid with constant buoyancy, frequency, and starting from linearized equations, derive the dispersion relation for the internal gravity waves given here. Okay, so we have W squared is n squared, k sub h squared over k sub h squared plus m squared, where here our k sub h squared equals that k squared plus L squared. Okay, so here we go. Letter A, for a Bussardesque stratified fluid with no rotation, here are the linearized equations. Okay, this is textbook stuff. Assume the normal modes. Okay, and then the buoyancy equation gives this. So B equals negative I n squared over omega omega. And using compressibility, we're given here. Okay, and then after eliminating pressure and velocity components, we wind up getting omega squared times the quantity k sub h squared plus m squared is n squared k sub h squared. So omega squared equals n squared times the k sub h squared over k sub h squared plus m squared. So it matches what originally we wanted to get. Okay, and now we want to just show that W is, that omega is less than n. Well, since that expression here, k sub h squared over k sub h squared plus m squared is less than 1, then automatically our omega is less than n. I could have added some to that, but I just wanted, this is like just a walkthrough, a quick overview of an exam, practice exam. So for C, for fixed horizontal wave number, determine what happens to omega as vertical wave number m approaches infinity. So as m approaches infinity, omega squared approaches that n squared k sub h squared over m squared approaches 0. So omega approaches 0. And for D, explain physically why internal gravity waves require stable stratification, and this is technically an internal gravity waves theme problem. So we could say, again, textbook conceptual answer here, canonical internal gravity waves require stable stratification because displaced parcels must experience a restoring buoyancy force. If n squared is greater than 0, vertical displacement produces oscillation. If n squared is less than 0, the fluid is convectively unstable instead. Okay, so hopefully I didn't misread anything, but the math there is correct, statements are correct, but I don't know if I'm correct with how I said it because I'm going fast trying to get it through this. 5, a shallow water fluid initially has localized height perturbation given by this hx 0 equals this with 0 initial velocity. Describe qualitatively the geostrophic adjustment process, and this is geostrophic adjustment problem. So letter A, this is canonical. Initially, the height perturbation creates horizontal pressure gradients but no velocity. Fluid begins accelerating from high pressure. Coriolis force then turns the flow. Part of the disturbance radiates away as gravity waves, while the remaining motion settles into approximate geostrophic balance. Okay. B, define the Rossby deformation radius, that L sub D equals square root of GH over F. Explain its physical significance. So right here, the Rossby deformation radius is just this, right? And what does it do? It measures the length scale over which rotation becomes important for free surface or interface displacements. So that is pretty much canonical. Letter C, if L is much larger than L sub D, rotation is very important. Much of the final state is balanced and geostrophic. If L is much less than L sub D, gravity wave dynamics dominate. The disturbance mostly radiates away rather than remaining as balanced geostrophic flow. And that's in relation to this, determine qualitatively how the final balanced state differs when you have those two properties. L much greater than L sub D, and L is much less than L sub D. Part D, canonical again. Why are gravity waves emitted during adjustment? So gravity waves are emitted because the initial state is not dynamically balanced. The system separates into a balanced geostrophic part and an unbalanced gravity wave part. So that's number 5. And now we can move along to number 6. Okay, so number 6 here for continuity stratified quasi-geostrophic fluid. The QG potential vorticity equation is given here. Okay. Explain the physical meaning of each term Q. So quasi-geostrophic potential vorticity. So we have here our formula, our equation, and here let's identify what we have. That del sub h squared psi is the relative vorticity. The F naught is the background vorticity. The beta sub y is the planetary vorticity variation with latitude. And then our partial here, d, respect to z. And then we have this quantity in parentheses, this F naught squared over n squared d psi dz. What's that? That is the stretching or stratification contribution to PV. Okay, so that's textbook stuff. Part B, derive the scaling assumptions required for quasi-geographic theory. So QG theory assumes that RO equals U over F naught L, much less than 1, much less than 1. It also assumes small fractional layer depth or isopsonal displacements. Okay, nearly geostrophic horizontal flow, hydrostatic balance, and weak agiostrophic motion. The leading order horizontal momentum balance is geostrophic. Okay, we have this, and we want to acknowledge that negative F naught G, negative F naught V sub G equals negative 1 over that rho naught here. And we have that F naught U sub G equals this quantity as well. The vertical balance is hydrostatic. Make sure we're differentiating between our rho and our P, our densities and our pressures. Here we have QG theory. Part C, state the conditions under which quasi-geostrophy breaks down. So QG theory breaks down when RO is not small. So not small. Near the equator where F approaches 0, in strong nonlinear flows, in convection, shocks, hydraulic jumps, or flows with strong vertical acceleration. That is where QG breaks down. Part D, why is QG theory so useful in large-scale atmospheric dynamics? So right here, QG theory is useful because it filters out fast gravity waves while retaining Rossby waves geostrophic balance, PV conservation, and baroclinic instability. It captures the slow balance dynamics of large-scale atmosphere and ocean flow. Okay, so that's number 6. Moving along to number 7. Whoops. Sorry. Old-fashioned setup here. Okay. 7. Barotropic and baroclinic instability. Letter A, state the Rayleigh. So this is all canonical. A through E here, textbook note stuff. Barotropic and baroclinic instability. Letter A, state the Rayleigh necessary condition for barotropic instability. So right here, a barotropic zonal flow, U of Y. Rayleigh's necessary condition for instability is that the absolute vorticity gradient changes sign somewhere here, where that beta minus U sub YY equals 0, somewhere in the domain, or more generally, that beta minus U sub YY changes sign. Okay. Letter B, explain physically how horizontal shear can destabilize a flow. Horizontal shear could destabilize flow because perturbations can tilt and exact kinetic energy from the mean shear. Extract kinetic energy from the main shear. The disturbance grows by transferring mean flow energy into eddy kinetic energy. So, letter C, describe the mechanism of baroclinic instability in a rotating stratified fluid. Okay, baroclinic instability occurs when sloping density surfaces store available potential energy. Perturbations displace warm and cold fluid parcels in a way that lowers the center of mass and converts potential energy into eddy kinetic energy. For letter D, using a thermal wind balance, explain why strong vertical shear is associated with horizontal temperature gradients. So here, thermal wind balance gives this equation, and this one, okay, that's canonical. Therefore, horizontal density or temperature gradients imply vertical shear of geostrophic wind. Think about what those symbols mean there. Textbook stuff there for D. And E, why are mid-latitude cyclones considered manifestations of baroclinic instability? Here, E, mid-latitude cyclones grow along strong horizontal temperature gradients. They extract available potential energy from the mean baroclinic state and convert it into eddy kinetic energy. So they are classical examples of baroclinic instability. Okay, so that's number 7. Hopefully I didn't talk too fast, but the answers are correct. Okay, and here. Okay, so we have a spur drop balance and western boundary currents problem here. So here, the vertically integrated vorticity balance in the ocean interior is approximated by spur drop balance. That beta V equals 1 over rho naught times quantity del times the cross product of del and tau sub Z, where V is the meridional transport per unit width and tau is the wind stress. Okay, part A, derive the spur drop balance from the vertically integrated vorticity equations. So here we go. The vertically integrated horizontal momentum equations are simplified for the ocean interior. Taking the curl removes the pressure. The dominant vorticity balance is between wind stress curl and advection of planetary vorticity. So you gotta get the right here what we were given, the spur drop balance. Then this V equals that cross product of V and tau sub Z over that rho naught beta. Okay, then it becomes ZV. Okay, then V, we could say V equals that rather. So B, explain physically why planetary vorticity gradients are essential for spur drop balance. Okay, so for letter B, this beta effect here allows meridional flow to change planetary vorticity, and without that beta, interior meridional transport could not balance wind stress curl in this way. Some people say meridional. Part C, why must western boundary currents exist in subtropical gyres? So right here, interior Sverdrup transport does not generally satisfy mass conservation and boundary conditions by itself. Return flow is required, and because of this beta effect and frictional vorticity balance, this return is concentrated on the western side. Okay. Part D, using vorticity arguments, explain why western boundary currents are narrow and intense. So we could say here, western boundary conditions are narrow and intense because they must carry a large return transport in a thin boundary layer. In that layer, friction or lateral viscosity becomes large enough to balance vorticity changes. So this is canonical, canonical, E. Also, textbook stuff. Discuss the role of friction in western boundary layers. So we could say here, friction allows the flow to cross geostrophic contours and satisfy no normal flow or no slip boundary conditions. Without friction, the gyre circulation could not close properly. Okay, so that's number 8, and moving along to number 9. Okay. Whoops, sorry. Okay, there we go. Number 9, we have Ekman layers or Ekman pumping problem. So consider homogeneous with eddy viscosity A sub V. A, starting from the steady horizontal momentum equations, including viscosity, demonstrate the Ekman spiral solution. So I'm just going to go through this. Let's just read letter B to define the Ekman layer depth and determine its scaling dependence on A sub V F. Sorry about the focus there. Okay. Hopefully we can get this back in focus. Okay, sorry. And letter C, show that the vertically integrated Ekman transport is perpendicular to the wind stress. Letter D, for northern hemisphere flow, determine the transport direction relative to the wind. And for letter E, explain the mechanism of Ekman pumping and its importance in ocean gyres. So, Ekman layers and Ekman pumping. So we could say here, the steady horizontal momentum equations with vertical viscosity are given here and here. Okay, with those second partial derivatives there. And introduce the complex velocity, this u equals u plus iv, then combine here at a sub v, second derivative u partial with respect to z minus a I f, and then times that u equals 0. The solution has the form u equals u naught e to the 1 plus I z over delta sub e. My apologies for my horribly drawn delta. For an ocean surface layer occupying z is less than 0, where, again, my apologies for the horribly drawn delta. Delta sub e equals square root of 2a sub v over f. Okay, Ekman depth scale. Okay, now the vertically integrated Ekman transports satisfies this negative f m sub y equals t sub equals tau sub x, f m sub x equals tau sub y. So therefore, we have here our partial, our m sub x equals tau sub y over rho naught f, and then m sub y equals negative tau sub x over rho naught f. So we get our m sub e here. Okay, that's our Ekman transport equals z hat crossed with tau over rho naught f. And this is up to sign convention depending on coordinate definitions. In the northern hemisphere, surface Ekman transport is 90 degrees to the right of the wind. Okay. All right, and here, Ekman pumping occurs when horizontal convergence or divergence of Ekman transport forces vertical motion. So this is the Ekman pumping velocity here, and that is the dot product of our del sub h, and that's dotted with our Ekman transport. And what we could say that here for the last portion. It connects surface wind forcing to the ocean interior and helps drive gyrus circulation. Okay, so that's number 9, and we move on here to number 10. This is the last one, and this is rather canonical for number 10 too. Textbook note stuff. Important though, very important. Synthesis problem. Consider a rotating stratified ocean basin forced by zonal and wind stress. Part A, describe the sequence of physical balances that determine the large-scale circulation from the surface Ekman layer down to the deep ocean interior. Okay, so letter A, surface wind stress drives an Ekman layer. Ekman transport causes convergence or divergence, producing vertical pumping or suction. That vertical motion forces the ocean interior, where the dominant balance is often as Sverdrup balance. Okay, as before, we saw this equation before, and the interior circulation then closes through intense western boundary currents and where friction becomes important. Part B, explain how potential vorticity conservation constrains partial motion in the basin. So for part B, potential vorticity conservation constrains motion through that Q equals zeta plus F over H. If a parcel moves northward, F increases. To conserve PV, either that zeta or H must adjust. This strongly restricts partial paths in rotating stratified flows. Part C, discuss how Rossby waves communicate information across the basin. Rossby waves communicate changes in pressure, height, and vorticity across the basin. Their westward phase propagation is caused by conservation. So their westward phase is caused by propagation. Their westward phase propagation is caused by conservation of PV on a beta plane. Sorry about that. Part D, explain how baroclinic instability can extract available potential energy from the mean flow. So, baroclinic instability extracts available potential energy from sloping density surfaces. Perturbations grow by converting mean potential energy into eddy kinetic energy, often producing large-scale eddies or cyclones. Okay, and final component here, letter E, describe qualitatively how rotation, stratification, wind forcing, and friction collectively determine the structure of subtropical gyres. So down here is letter E. Rotation produces geostrophic flow. Stratification supports baroclinic structure and thermal wind shear. Right here, the wind stress drives Ekman transport and Sverdrup interior flow. The beta effect organizes the gyre and favors western intensification. Friction closes the circulation in boundary layers. Together, these effects produce broad, weak interior flow and narrow, strong western boundary currents. Large-scale GFD is governed by balance, conservation, waves, and boundary layer closure. So this is canonical textbook stuff, very important information for number 10. Always good to know, and sorry for going through it so fast. Just wanted to get you through this, and so you have a reference for some extra practice problems, practice-free response if you're getting ready for an exam of this nature. So this was the practice exam on geophysical fluid dynamics. Thank you, and have a great day.